Hey everyone, and welcome back to the teaching streams. It's been a whole 24 hours. We're rested, we're relaxed, and guess what? We're going to be doing some operating systems again today, and we're going over none other than the Dinosaur book, Operating System Concepts. I'm pretty sure everyone uses this book at some point or another, except I actually didn't. I used Operating Systems Principles in Practice, but I wish I used the Dinosaur book. It's way cooler if I can just call something the Dinosaur book. But hey, we're not going to complain here on the stream. We're going to have a wonderful day. We're going to learn some operating system stuff. And we're here, of course, to have some fun. Let's get started. Alright, and here we are. The production value, I know. Listen, we're working on it every single day. We're trying to get this to be more and more professional. I think we can make it. Eventually we'll have a streaming PC of our own, and eventually we'll be able to do cooking streams, which is that's what this channel's really about, right? We want to see me cook something, or maybe play cello, or maybe play tennis or something. I don't know what you guys want. But guess what? We've got the Dinosaur book again today. And this is going to be a lot of fun. Where's my cursor? Let's maximize it. Let's zoom it in. What did we go over last time? We introduced operating systems, didn't we? That was fun. We got to see some basic things that operating systems do. What else did we do? We went through the boot procedure. So how does a computer boot up? We showed that we typically have some abstraction, where operating systems are kind of in the middle between application software and hardware, and generally in this system software range. And we kind of just described operating systems and some common ones that are out there today, some open source ones, some closed source ones, all this kind of fun stuff. But guess what? We're going to get more in depth today. We're going to talk about operating system structures. So we're going to get more into, what an operating system does and how do they work internally. Now this is going to be fun. I remember I took just last semester I took an operating systems class, and we got to muck around in the Linux kernel. We were playing around in it was kind of an older kernel. What was it? It was 3 dot something. 3.18 maybe? Is that one? Yeah, we were mucking around in an old Linux kernel. That was a lot of fun. Maybe we'll show that sometime. There's actually simulators for hardware, all the way up to the operating system level. So you can simulate a 32-bit Linux kernel or 64-bit Linux kernel on like an ARM hardware in a simulator. That's really cool. I had fun with that class. So let's get started. So what does an operating system do? It provides the environment where programs are executed. So we want, some abstraction between the hardware and the software that, does all the nasty stuff like interacting with the hardware. So that programmers of applications don't have to worry about that. So they vary greatly, of course, and we saw that when we talked about the difference between Windows and Linux. We see that, there's different file systems that are used, whether it's FAT or NTFS. Tons of different options there. I used to have an anecdote about NTFS, but I don't think I have it anymore. It was something about, for the longest time, they were working on reverse engineering NTFS to be able to support it in Linux. But I think they eventually did, but it took forever. Excuse me. Let's take a sip of my protein. We just got back from the gym. We had a lovely time there as well. Okay, it's important that the goal of this system be well defined before the design begins. The same as any good design. We want to make sure that we have things well defined before we start cutting. Measure twice, cut once. These goals form the basis for choices among various algorithms and strategies, of course. So what are we going to do in this chapter? So what should we learn? What should we learn? So we should learn to describe the services an operating system provides to users, processes, and other systems. So we'll see that these vary depending on who's talking with the operating system, whether it's another system or user or process. We'll discuss various ways of structuring an operating system. So we'll see that not all operating systems are alike. We'll explain how operating systems are installed and customized and how they boot. So this doesn't mean we're going to run through, hey, how do I go through the installation wizard on Windows or Ubuntu? So it's going to be a little more interesting than that. Okay, so let's start. Operating System Services 2.1. We're in the dinosaur book. So here we have an operating system provides an environment for the execution of programs. Yes, we know this. The specific services provided, of course, differ from one operating system to another, but there's some commonalities. These operating system services are provided for the convenience of the programmer to make programming task easier. So 2.1 shows one view of the various operating system services and how they interrelate. So we have up here all the user and other system programs. We have things like the GUI, the command line, batch, and then we have some user interfaces. And so we'll see that we can use system calls to access some other services. So program execution, I/O operations, accessing the file system, doing things like communication, resource allocation, and accounting. And then we'll see we'll have some other services in here, such as error detection and protection and security. And we'll see that all of this is confined within the operating system. So let's start defining things. So the user interface. So almost all operating systems have a user interface. Well, that's convenient. If we have an operating system, typically we'd like to work with it at some point. So one is the command line interface. So if you're a hardcore programmer or coder, you think that you can never use a GUI, right? So most people like the command line interface, and it is better for some things. So if you're you're moving through directories or you're searching directories, oftentimes using the command line can be faster. Let's see. So another is a batch interface, in which commands and directives to control those commands are entered into files, and those files are executed. So here we have another interface where we basically just write some files and they do some things for us, similar to writing commands, but we're putting into files instead. And then we have what most everyone knows and is familiar with, the graphical user interface. So then, of course, we have program execution. So we should be able to load a program into memory and then run the program. It would be pretty pointless to have an operating system that can't, execute any programs. We want to support I/O operations. So a running program may require input and output, which may involve, either a file or an I/O device. Doesn't matter what it is. If we're recording something like a CD or a DVD, or we're playing music and we want to use a CD or a DVD as input, we need I/O. We want to do some file system manipulation. So obviously we need to read and write files and directories, but it'd be nice if we could create files and delete them, do things like searching and listing file information. All of these things are, we take them for granted, but at some point or another, somebody had to say, hey, this is what an operating system needs to do. Let's specify it out and make sure it gets included. Typically, we want to do some kind of communication. So there are many circumstances to which one process needs to exchange information with another process. A trivial case is something like a, inter-process communication. So if you have I'm actually working on a big simulator right now where, because it's this massively disaggregated supercomputer simulator, all these different components are different processes, but you want to be able to talk to each other, so you have to use some kind of inter-process communication. So you generally have two options, which is shared memory, which is what the simulator that I do works with, or you have something called message passing, where you send packets of information in predefined formats. So shared memory is basically, it's just a region of memory that two different things can write to. Two different processes, that is. And then we want some error detection, of course. We want to make sure that if something goes wrong, well, we can tell that something went wrong. So errors may occur in the CPU, memory hardware, such as a memory error or power failure, I/O devices, a failure on a network, or lack of paper on a printer. There's 1,000 things that could go wrong. There's even some simple things like arithmetic overflow. So if we try to do some operation and we get an illegal value, well, we want to be able to tell if, we did something illegal. We also like to tell if someone tries to access a legal memory location. And this is actually a funny thing because NVIDIA doesn't care if you access illegal memory locations. They don't fail or do anything. Isn't that interesting? They don't really care about security. At least for now. They assume mainly exclusive execution though, so you generally don't need to protect yourself from yourself. Okay. Yeah, so we want to do some error detection as well. So another set of operating system functions that isn't specifically for helping the user, but we want to make sure that our operating system is acting efficiently, are things like resource allocation. We want to make sure when we have multiple things running at the same time that someone isn't hogging say all the I/O bandwidth, all the memory bandwidth, all the compute time on the CPU. We want to make sure that we have some CPU scheduling routines or something that trades off, where it says, okay, well, you've had your fun, now hit the road. I'm taking over now. And so this was actually a project that I had in a class of mine where we designed and we built a it was a scheduler based upon the completely fair scheduler, which is the actually implemented scheduler in the Linux kernel. So, that's what we're talking about here when we're talking about resource management. That's one of the things, at least. So then we want to do some accounting. So we want to keep track of which users use how much and what kinds of compute resources. And so this is used for accounting so that users can be billed, or maybe just some usage statistics. You can also think of this as this would be useful for quality of service. If we want to guarantee that say Bill gets 30% of the compute power and Dave gets 30% of the compute power and then Jan gets 40% of the compute power, well, you have to have some way of measuring how many resources is everyone taking. So we want to do some accounting. And then of course, we want protection and security. So we want to make sure that information from multi-user systems or networked computer systems, we want to make sure that they're protected and that we have control over the resources so that someone can't just run in and say, hey, I'm just going to read all the memory, is that all right? And then they do it anyway. We want to make sure that doesn't happen. Okay. And this starts at user authentication, by logging into a system with a password, but it goes all the way to the memory system of marking things as readable by which users. And then of course they talk about a common thing to think about, which is a chain is only as strong as its weakest link. So we want to have this this complete full stack solution for security. That way if you're talking about someone logging into a system, if someone can trivially log into a system, like what was the Apple thing where you could log in as an administrator, and I think it was just like you type in like admin and then you didn't type in a password, you could log in. I think that was the High Sierra bug, if I'm remembering correctly. It doesn't matter if you have all these other security measures. If someone can just log in as an administrator, well, who cares? You're already compromised. So we want to think about this as, an entire link of security, from top to bottom. So now let's talk about the user and operating system interface. Man, I've been trying out this protein powder, and it has like flax seeds in it. And sometimes they just get stuck in your throat. Okay. So let's see. So we mentioned earlier there's several ways for users to interface with the operating system. So one provides a command line interface or command interpreter. So generally we just call this, shell or something, or, like the bash, which is the born again shell. So the other allows the user to interface with the operating system with a graphical user interface, or GUI. So we've got a couple options here. So let's talk about shells again, or maybe for the first time. If this is your first time learning about shells, welcome to a wonderful world. I use them every single day. So some operating systems include command interpreters in their kernels. Others, such as Windows and Unix, treat the command interpreter as a special program that is running when a job is initiated or when a user first logs on. Okay, so on multiple command interpreters to choose from, the interpreters are known as shells. So like I said, when we're talking about a command line, generally we refer to it as a shell. So in Unix and Linux systems, there's a lot of different options. There's the bourne shell, C shell, born again shell, often called bash, B-A-S-H. And then there's the corn shell. I've only ever used bash, really. Third-party shells. I actually built a shell once. That was the first project in that operating systems course. We had to build a shell, and we had to implement some common shell functionalities. Okay. So third-party shells and free user-written shells are also available, but hey, it's free user-written code. We don't care that much. We care about what we actually use. I mean, if you design a shell and it's really good, I care. Send it to me. We'll use it on stream. So most shells provide similar functionality, of course, but it's usually personal preference. So they show a Solaris 10 example, but who cares? So the main function of the command interpreter, or shell, is to get and execute the next user-specified command. We can skip most of this. Basically, a shell is just used to execute commands. And oftentimes, so like in Unix system, among other, it implements most commands through system programs. In this case, the command interpreter does not understand the command in any way. It merely uses the command to identify a file loaded into memory and executed. So if we were to remove a file, so RM stands for remove, so remove file.txt, it would search for a file called RM that's in some path that it's already known to bash or the shell. Load that file into memory. That's how we execute things. So we have to load it into memory, then execute it with the parameter file.txt, and then whatever RM does, remove, it executes, whatever, it's an executable. It's just an executable. It runs and it'll remove the file. So let's talk about GUIs now a little bit. Everyone's familiar with GUIs, so this shouldn't take long. So GUIs are pretty simple. We've got desktop, we've got icons, and we have folders, which are basically just directories. One of the things that people often misattribute to Apple is that they created the first GUI. They didn't. They stole it from Xerox. They stole it from Xerox, and then Microsoft stole it from Apple. So, everyone steals from someone. But, you have to implement it at the end of the day. Just because you get the idea, if no one's doing anything with the idea, then, hey, it's their loss. That's actually the funny story of how, I think it's how... So here's an interesting story. I heard this from a lecture that I had. It was just a guest lecture. And it was about Microsoft and the starting of Microsoft. And what happened was... I think it was IBM. IBM was looking for an operating system, right? They were just like, hey, we need to get an operating system. What do we get? And so there was some guy in Silicon Valley or something, or it wasn't really Silicon Valley at the time, but there was some guy out there in California, and he had some operating system, right? And so the guys from IBM, they try to track him down, and they're just like, hey, we want to buy this from you. But he decides to blow off a meeting with them, and he goes flying in his like private plane, and he just blows off the meeting. And so they look around and they go, hey, there's some guy called Bill Gates, and he's doing some kind of thing like this. And so what they do is they go over to, they meet with Bill Gates, and they say, hey, we wanted something like this. Is this something you could do? And he says, absolutely. Not having the product at the time, but he just says, absolutely. And what he does is he spends, I forgot how much money it is, but it's in the thousands. He spends like $10,000 or maybe $20,000, buys some operating system that somebody had, and then just spruces it up, and then he sells it to IBM. And that's how Windows got started. That's, it's this weird turn of events. Okay, is there anything else in here? Not really. They talk about KDE and they talk about iPad, touchscreen. That's fine. So let's talk about choice of interface. So when you use command line or GUI, so system admins or sysadmins who manage computers, and power users who have a deep knowledge of the system. Hey, are you guys power users? Do you guys use the shell? Frequently use the command line interface. It is more efficient and it is faster access to certain activities. If you ever tried to, I don't use a Windows machine anymore, but if you've ever tried to like search for a file on like a Windows machine, it's a nightmare. Yeah, so you can automate some repetitive tasks with shell scripts, which is nice. So in contrast, most Windows users are happy to use the Windows GUI environment and almost never use the MS-DOS shell interface. Although, I heard recently that Microsoft was making their own like Linux kernel. What's that about? So we can skip the rest of that. We don't need to talk about Windows, and we don't need to talk about using a shell. That's not that fun. So let's talk about something a little more interesting. Oops, dropped my pen. Let's talk about system calls, or syscalls. So what do system calls do? They provide an interface to the services made available by an operating system. So services made available by an operating system. So they're generally available as routines written in C and C++. Although certain low-level tasks, for example, where the hardware can be accessed directly, are written using assembly language instructions. So you can look at a lot of these things. If you just go on that site I've shown before, it's an amazing site. If you ever want to just play around and look at some of these things, you could always just go to, I think it's like elixir.bootlin. And this actually has the entire Linux kernel on it. But then you can also like get down to the assembly level stuff. Let's see. Boot maybe. They have everything, including like the assembly in here. Well, they have everything. Yeah, so here's all ARM assembly. So everything's on this site, and it's really great. It's a great site if you ever need to work on the Linux kernel. But let's get back to operating systems. All right. So before we discuss how an operating system makes syscalls available, let's illustrate how a system call is used. So writing a simple program to read data from one file and copy them to another file. So a pretty simple operation, but a very common one. The first input that the program will need is the names of the two files. Well, pretty simple. So we need the input file and the output file. and these names can be specified in many ways depending on the OS. So one approach is the program to ask the user. In an interactive system, this approach will require a sequence of system calls. First to write a prompting message, then read from the keyboard, and then to get the characters. But on like a mouse-based system, an icon, you'll have a menu of file names, and then you'll like double-click. So pretty simple. So once the two file names have been obtained, pretty simple first step, the program must open the input file and create the output file. Each of these operations requires another syscall. Possible error conditions for the operation can require additional syscalls. So we want to make sure that we're not doing something illegal. So we want to make sure that we're not writing to a read-only file, for example. So when the program tries to open the input file, it may find that there is no file of that name. So pretty simple, a naming error. Or that the file is protected against access. So maybe that user doesn't have the privileges to open that file. So in these cases, the program should print a message to the console. So this is just enforcing that idea of, there's a lot of cases that we need to cover. So if the input file exists, so the good case, then we must create a new output file. But we need to figure out if there already is an output file with the same name. And so the system may cause the program to abort, or we may delete the existing file. So I know in Python, if you do a write to a file name, it basically just creates a new file. It overwrites that file with nothing, and then you start from scratch. Or if you do append in Python, it just tacks it onto the end of that file. I don't know if it has any failing things. Okay, so another option is an interactive system, which is to ask the user via sequence of system calls, prompting message from the terminal whether to replace. So just handling some cases of whether the file exists or not. So this is when you get that pop-up saying, hey, or when you're trying to copy things from one folder to another, and you get the pop-up message that says, hey, we noticed that these have the same name. Do you want to not copy it, or do you want to overwrite it? So when both files are set up, so we're finally at the point where we have both files, we enter a loop that reads from the input file, a syscall, and writes to an output file, another syscall. So a read and a write syscall. So each read and write must return status information, regarding various possible error conditions. On input, the program may find that the end of the file has been reached. Where is it? End of file. Usually with like an end of file character, or that there's a hardware failure in the read, such as a parity error. The write operation may encounter various errors depending on the output device. For example, no more disk space. So we probably shouldn't try to write if we don't have any more space, because we're probably going to overwrite something. So finally, we've gotten to the point, we've opened files, we've started this copying process, but we eventually hit the point where the entire file is copied, and the program may close both files, another syscall, write a message to the console window, another syscall, or more syscalls, and then terminate normally. So a final syscall. So we see we have a ton of syscalls here. Just to move from some source file to a destination file, if we're doing things like acquiring, writing, accepting input, getting a file name, writing, please input a file name, access the input, open a file, check if it doesn't exist, create a file, check if it exists, loop, read, write, check to see if we get a failure. If we don't get a failure and we've hit the end of file character, close, write completion, and terminate. We've got a lot of syscalls to take care of. But fortunately, they're not too difficult. So even for a simple program, this can be, heavy use of the operating system. This isn't something that's only in like the user space or rather the application space. We need the operating system. So frequently systems execute thousands of system calls per second. So most programmers never see the level of detail. However, typically application developers design programs according to an API, otherwise known as an application programming interface. And the API just says, here's a set of functions that are available to an application programmer with parameters that are passed that the programmer can expect. So it's basically saying, here's a guideline for how to use this. So 3 of the most common APIs are the Windows API, which I've never used or even looked at. There's the POSIX API for POSIX-based systems, which include virtually all versions of Unix, Linux, and Mac OS X. And then the Java API, which I've never looked at the Java API either, honestly. A programmer's access to an API via library code provided by an operating system. So we've got a library of code that we look up. In the case of Unix, Unix and Linux, for programs written in the C language, the library is called libc. So typically, if we want to do some syscalls or if we want to do syscalls in some system software that we're writing, we have to include libc. So note that unless specified, the system call names used throughout this text are generic examples. Each operating system has its own name for each system call. Okay, a little disclaimer there. That's fine. So why would an application programmer prefer programming according to an API rather than invoking the actual system calls? So this is an interesting question. So apparently there's several reasons for doing so. So let's look at 1, program portability. This is nice. Generally, we don't want to have to write our program again whenever we get to a new piece of hardware. I personally don't like doing that. I work with GPUs. There's nothing more annoying than running code on a different GPU because you have to re-optimize it. Because your code is written catered towards the architecture, which is annoying. It's annoying, but hey, you get good performance, I guess. So an application programmer is probably just going to say we don't want to have to. It's just saying that if we use an API, we can expect the program to compile and run on any system that supports the same API, which is good. So furthermore, actual system calls can be more detailed and difficult to work with. So, as a programmer, you want to make your job easy. If you have some abstraction layer that makes things easy, you better have a pretty good reason in order to, bypass that abstraction layer. So nevertheless, there often exists a strong correlation between a function in the API and its associated system call within the kernel. In fact, most of the POSIX and Windows APIs are similar to the native system calls provided by Unix, Linux, and Windows OS. So APIs, they're all different, but at the end of the day, they're all implementing the same kind of thing. If we're trying to open a file, for example, is that really going to change much across different systems? Probably not, but it's nice to have it anyway. Okay. So what was this example they give? Standard API. Okay. So as an example of a standard API, consider read. That is available on Unix and Linux. The API for this function is obtained from the man page, so you can just do man read on your own time. So we have a return value of some size t. We have a function name, of course, read, and then the parameters, a file descriptor, generic pointer to a buffer, and then some size. So yeah, the file descriptor, a buffer to read data into. Notice that it's a void pointer. So void pointers, if you're not familiar with them, the reason why they don't have a type associated with them, and they're a void type, we often call these generic pointers because they can point to anything. And they're convenient. They're a convenient thing to work with. And then we have size t, count, which is the maximum number of bytes to be read into the buffer, which is nice. And then of course we have some return value, which is the number of bytes read. A return value of 0 indicates end of file, and then if an error occurs, as with most functions, it returns a -1. Okay. So for most programming languages, the runtime support system, a set of functions built into libraries included with a compiler, provides a syscall interface, or a system call interface. I'll just abbreviate it as syscall. That's what most people say. So the syscall interface intercepts function calls in the API and invokes the necessary system calls within the OS. Typically, a number is associated with each system call, and the system call interface maintains a table indexed according to these numbers. So the system call interface then invokes the intended system call in the operating system kernel and returns the status of the system call and any return values. So let's see what happens. So if we're in some user application and we're calling some API for open, we go to the syscall interface, and so notice we're in user mode up here, and we use the this API in order to access functions that work in the kernel space. So in kernel mode, the actual syscall comes down. It accesses some vector that it talked about here, some table rather, which points to, at whatever syscall that we're trying to run. It finds the implementation of open, it executes this code, and then it returns. We go back to the syscall interface where it just gives the value, and then it goes back to the user application. So we see we got rid of a lot of, there's a lot of layers of abstraction here. So the user application never needs to see anything about this table lookup. It never needs to see anything about how open is actually implemented on the hardware. All it sees is I called something called open. I got a response back. Nice, clean, neat. So the caller need know nothing about, okay, so this is what we just talked about. The caller doesn't need to know anything about the hardware. So 3 general methods are used to pass parameters to the OS. The simplest approach is to pass the parameters in registers. In some cases, however, there may be more parameters than registers. In these cases, the parameters are generally stored in a block or a table in memory, and the address of the block is passed to the parameter. So this is kind of similar to something called register spilling. So typically, if you can't store everything in just the registers, you spill them out to memory, hence why it's called spilling. So parameters can also be placed or pushed onto the stack by the program and then popped off the stack by the OS. So some operating systems prefer the block or stack method because the approach does not limit the length of the number of parameters being passed. So if we do it, say, in the registers, then we're limited by how many registers are defined in our architecture. Okay, so here's how we pass parameters as a table. So what we do, so we load all of our parameters into some table, and then to some register, we load the address that points to these things. Okay. So now that we've talked about system calls generally, and we've talked about, user interfaces, it's about time that we talk about some other stuff. So let's talk about types of syscalls. So not just how syscalls are implemented, some different types of them. So what do we use them for? A lot of things we talked about previously. So process control, file manipulation, device manipulation, information maintenance, communication, and protection. So let's go ahead and start at process control. So a running program needs to be able to halt its execution either normally with end or abnormally with abort. Generally, we don't want some piece of code to execute and then just run through whatever's next, other instructions it can find. We want it to stop. We want it to quit. If something goes wrong, we also want it to quit and call abort. If a syscall, is made to terminate the currently running program abnormally, or if the program runs into a problem, so abnormally or runs into a problem, it can cause an error trap. A dump of memory is sometimes taken, and an error message is generated. The dump is written to disk and may be examined by a debugger, a system program designed to aid the programmer finding and correcting errors or bugs. Okay. So, you can think of using something like GDB, which I should probably make a video on. GDB is an invaluable tool if you're trying to debug stuff. Doesn't help too much if you're working on hardware with operating systems, because if you do something wrong when you're hacking around in an operating system, it won't boot. So you won't get much help there. So under either normal or abnormal circumstances, the OS must transfer control to the invoking command interpreter. The command interpreter then reads the next command in the interactive system. The command interpreter simply continues with the next command. It is assumed that the user will issue an appropriate command to respond to any error. In a GUI system, a pop-up might alert the user that there's an error and ask for guidance. So it might go, hey, you entered an incorrect value. Do you want to try again? So in a batch system, so batch systems are file-based, the command interpreter usually terminates the entire job and continues with the next job. So, because there's no, direct contact with the user, because it's files that we're executing, it'll just quit, find something else to do. So the system may allow for some special recovery actions if an error occurs. If the program discovers an error in its input and wants to terminate abnormally, it may also want to define an error level. So more severe error levels can be indicated by a higher level error parameter. Okay, so what do we have here? So types of syscalls. So we're going to be going over these, so we can kind of skip this table. In fact, we are going over these right now. Okay, so the command interpreter or a following program can use the error level to determine the next action automatically. So if we define some error level to see if this error happens, if that error happens, we can do something different. So this gives us a little bit of flexibility in the case something goes wrong. So the process or job executing one program may want to load and execute another program. So generally we like to run things, so we'd like to be able to load them and also execute them. So this feature allows the command interpreter to execute a program as directed by, for example, the user. A user command, the click of a mouse, or a batch command. So an interesting question is where to return control when the loaded program terminates. This question is related to whether the existing program is lost, saved, or allowed to continue execution concurrently with the new program. Interesting. So let's see, example of Windows and Unix syscalls. So, for process control, in Unix we generally call, when we want to create a process, we generally call it a forking, and we make a child process. But in Windows, it's just create process. It seems like they're a little more explicit in Windows, so exit process instead of exit, wait for a single object instead of wait, create instead of open, read read file instead of read. And the other interesting ones, it seems like they really just enumerate, what this stands for. So get current process ID versus get PID. Yeah, I mean, I guess it seems like a waste of time, but hey. Also, the capital letters, come on, use lowercase letters. Don't have to hold down shift. Okay. So what happens when we start executing a different program while another program's executing? So what happens when that program finishes? So if control returns to the existing program, when the new program terminates, we must save a memory image of the existing program. Thus, we have effectively created a mechanism for one program to call another program. If both programs continue concurrently, we've created a new job or process to be multi-programmed. So multi-programming, multiple programs running at the same time. Often there is a system call specifically for this purpose. So things like create process or submit job. Okay, so we're talking about controlling these jobs now. So this control requires the ability to determine and reset the attributes of a job process. So things like priority, maximum allowable execution time, all of these attributes that we want to kind of control for fairness, we have to reset them. We may also want to terminate a job or process that we created. So if something goes wrong, or if we know something went wrong, or if we realize even if the program is executing and won't crash, maybe we realize that, hey, I should change this in the code. We want to be able to kill that program. So we have another syscall, this terminate process, to do that. Okay. So the standard, let's look at this example real quick, which is going to be an example of standard C library. Okay. So the standard C library, let's see, an example, let's assume a C program invokes printf. So we want to print something to the screen. The C library intercepts this call and invokes a necessary system call or calls to the OS. So in this instance, the write system call, because we want to write to the screen. The C library takes the value returned by write and passes it to the user program. So let's see what happens. So up here we have, stdio.h. We have, what's his name in chat? Is it, how do you pronounce his name? Is it Coronatius? Every time I say hi in chat, he says greetings, so he'd appreciate this. So if we're doing something like a printf, this is going to go to this API for the standard C library. It's going to invoke a write system call. The OS is going to take care of this write, and then it'll return some value to the user, whether it succeeded or not, and whether it has any return values. Okay. So having created a new job or process, we may want to wait for them to finish their execution. But, sometimes we're impatient. Sometimes we don't want to wait forever. So we may want to specify a certain time. So something like wait time, or wait for a certain event, so wait event. And then whatever's going on, it should do something like signal event. So if we're waiting for an event, well, an event should be signaled at some point. And this is an interesting problem that, or an interesting section dealing with consistency that we often need to think about, which is locks when we're talking about shared data. So to ensure the integrity of data being shared, operating systems often provide system calls allowing a process to lock shared data. So if multiple users can access some data, we don't want these writes or reads to come in the wrong order. If somebody is writing to the data, we don't want someone to read a stale value. So we have to lock that data, wait for a write to complete, and then release the lock. So we want to be able to acquire locks and release locks. Most of the time we don't need to worry about the implementations of these things, but it's good to know that they exist. Okay. So 2.9, MS-DOS execution at system startup and then running a program. So let's compare the differences. So what happens? So what we end up doing is we load some process into memory when we want to execute it. Okay. Makes sense. So because MS-DOS is taking single tasking, it uses a simple method to run a program, which does not create a new process. It just loads the program into memory, writing over most of it to give the program as much memory as possible. Next, it sets the instruction pointer to the first instruction of the program, so we want to make sure we're starting at the beginning, so wherever we loaded that into memory. So following this action, a small portion of the command interpreter that was not overwritten resumes execution, and its first task is to reload the rest of the command interpreter from disk. So we push out some of the command interpreter, this top chunk here, to make room for the process. And then when the process is finished executing, we say, hey, get that stuff back from disk. So FreeBSD is an example of a multitasking system. So by multitasking system, we have, some interpreter in here, but we have multiple processes going on at the same time. So the command interpreter may continue running while another program is being executed. So to start a new process, the shell executes a fork system call. So a fork just creates a child process. Then the selected program is loaded into memory via execute. So generally what happens is you'll have, generally what you'll do is you'll have a fork. It checks to see if it's a child process. If it is a child process, it will execute. And then if it's not, it'll do something else. Okay. So depending on the way the command was issued, the shell then either wants to wait for it to finish or runs a process in the background. So in the case of, say, a command line, if we are executing or we're writing something in Vim, right? We'll make that a child process, but we want the main bash to kind of hold put while we've got Vim up on the screen. But if we do something like Control Z and we put Vim to the background and now it's a background task, well, we want it to still be there. We don't want to just kick it out. So that's what this situation kind of relies on. So we check. This depends on what the parent process does. So whether it spins or it continues going. So when a process is running in the background, it cannot receive input directly from the keyboard because the shell is using this resource, this I/O. So if we kick something to the background and we type again, so if we are in Vim, press Control Z and start typing again, well, we're not typing into Vim anymore. So when the process is done, it of course calls an exit. And though in Chapter 3, we'll see a program example using fork and the execute system calls. Okay. So now let's talk about file management a little bit. So we need system calls for creation and deletion. It'd be nice to open things, to write, maybe reposition wherever we're writing in that file. And then we also would like to close the file when we're done with it. It may also be nice to have system calls to get attributes about the file or maybe even set attributes about the file. And then maybe moving and copying is something we'd also like to do to files. I think we'd like to do that to files. But as we can see, file management, fairly intuitive. Device management. Let's talk about device management next. So similarly, we're going to need, open and close with devices. So we want to open a device and we want to close the device when we're done with it. So various resources controlled by the OS can be thought of as devices. Some of these devices are physical devices, so things like disk drives. But we can also have virtual devices, so like files. So a system with multiple users must, we have to have syscalls for requesting a device. So if we have multiple users trying to use maybe one device, well, we want to make sure that we don't just steal it away from someone while they're using it. We want to have some syscall in place to request that device when it becomes available. So that's that thing of ensuring exclusive use. And then, of course, we want to release it when we're done with it. So similar to open and close, request and release. Okay. So once a device has been requested and allocated to us, we can read, write, and possibly even reposition the device as we can with files. So the similarity between I/O devices and files is so great that many operating systems, including Unix, merge the two into a combined file device structure. So things like file descriptors. In this case, a set of syscalls can be used on both files and devices. Sometimes I/O devices are identified by a special file name, directory placement, or file attributes. Okay. So let's talk about Information maintenance. Something possibly a little bit different. So we've talked about some simple things, some opening and closing and printing, and how we may translate those to syscalls. But now let's talk about something that may not be as intuitive. So something like information maintenance. So many system calls exist simply for the purpose of transferring information between user program and the operating system. For example, most systems have syscalls for things like getting the time, getting the date. These are things that are just in the OS, so it makes sense to have a syscall for them. So other syscalls may return information about the system, so number of users, version number, the OS, the amount of free memory or disk space. So we want some other way to latch in and get some information about resources. But when we're debugging, we'd also like to have some interface to get some useful information. So most systems provide a dump of memory. And so here we're talking about a program trace that lists each syscall as it is executed. Even microprocessors provide a CPU known as a single step in which a trap is executed by the CPU after every instruction. So in something like GDB, you can single step instructions, I'm pretty sure. CUDA GDB allows this as well. So you can actually single step instructions on the GPU as well. And then the trap is usually caught by the debugger. So many operating systems provide a time profile of a program to indicate the amount of time that a program executes. This presents a security hazard, as you may or may not have guessed. So typically, I forgot what the instruction is that allows for this, but you can get like sub nanosecond time granularity from instructions on computers now, which provides you, at first thought you go, wow, that's amazing. But on second thought, if you're concerned about security, you go, wow, if someone wants to do a correlation timing attack, they have a really, really clear way to get timing information. So a lot of people have actually exploited that. Okay, let's continue on. So in addition, the operating system keeps information about its processes and system calls are used for information. Generally, calls are also used to reset the process information. So things like get process attributes and set process attributes. Okay, and we'll talk about those in the next chapter. Okay, let me respond to a message real quick. All right. Take a sip of protein and get back to talking about the dinosaur book. Let's get to communication now. So we're still in things we've seen a lot before. I'm trying to think if there's maybe communication might be something that could be fairly new. Yeah, it's fairly new to most people. Most people can understand the idea of opening and closing and printing and getting file attributes. But communication is something that may be a little more abstract. So we're talking about two things, the shared memory model and then in the message passing model for communication. So in the message passing model, the communication process exchange information from one to another. Messages can be exchanged between processes either directly or indirectly through a common mailbox. So when we're talking about message passing, the general model is, okay, there's a common mailbox, we send a message to it, and then the other guy reads that message. In the case of shared memory, both people can, the data that they're actually working on, they can change it. So it's a little bit different. So before communication takes place, a connection must be open, the name of the other communicator must be known, be it another process on the same system or on another computer connected over a communication network. So this is the case of what I'm doing. So on a supercomputer, you have many, many, many different servers. So you may not be residing on the same machine. So this is directly related to the stuff I do, actually. So each computer and network has a host name by which it's commonly known. And then a host also has a network identifier. And then similarly, a process has a process name. And then that name is translated into an identifier by which the operating system can refer to that process. So things like get host ID and get process ID do this translation. So the identifiers are then passed to the general purpose open and close calls to provide the system with some specific, open connection or closed connection syscalls, depending on the system's model for communication. So the recipient process must usually give its permission for communication to take place with an accept connection. So, there's some back and forth going on here. We want to open a connection, but then the other guy has to actually accept it. If it just automatically accepts it, well, it seems like that could probably be a security hazard. So most processes that will be receiving connections are special purpose daemons, which are system programs provided for that purpose. They execute a wait for connection call and are awakened when a connection is made. The source of the communication, known as the client, and the receiving daemon, known as the server. So client and server. Then exchange messages using read message and write message syscalls, and close connection terminates it. Okay, nothing too special there. We have to request connections, wait for connections, and then accept connections. Then we can read messages and write messages. Pretty simple. So what happens with shared memory now? So now we're not working with this mailbox interface. Now we're working with actual shared memory. So processes use shared memory create or shared memory attach syscalls to create scroll down. To create and gain access to regions of memory owned by another process. Recall that normally the OS tries to prevent one process from accessing another process memory. So shared memory requires that two or more processes agree to remove this restriction. So then they can exchange information by reading and writing data in shared areas. So instead of having a mailbox where we have to pack a message and send it over, now we just have these little pools of memory where we say, hey, if it's Bill's pool, he may see Frank over there and he goes, hey Frank, you want to come to my pool? Then they share that pool so they can both use it together. They don't have to write each other letters now. And so we have to make sure that we're not doing silly things like we're not writing to the same location simultaneously. And we'll talk about that when we get more into things like locking in chapters 5 and 4. So, protection. So we've gone through, what have we gone through now? We've been through opening files, messing around with files, doing some communication, information maintenance, managing devices. Anything else special? Not really. Some simple stuff. So now we want to get to protection, security. Okay. So protection provides a mechanism for controlling access to the resources provided by a computer system. So we're going to have some special syscalls here, like we want to set permission levels. We want to also get permission levels. And we want to basically want to be able to manipulate permission settings for resources like files and disks. And we also want some things like maybe allowing users and denying users access to certain resources. And so this will be something we'll talk about way later in chapters 14 and 15. Okay, so we've talked about syscalls. A lot of information there. So let's get something. What do we do with syscalls? Well, generally we write system programs with them, so system software. So what is system software? The $1 million question, isn't that right? Everyone wants to answer the $1 million question. So another aspect of a modern system is its collection of system programs. Recall from figure 1.1, which depicted the logical computer hierarchy. At the lowest levels, it's hardware, and then you've got the OS and system programs, and finally the application programs. So system programs or utilities provide a convenient environment for program development and execution. So some of them are simply user interfaces to system calls, but others can be pretty complex. And then, of course, we can divide these into categories. So things like file management, other things like status information. So if someone wants to ask for the system for the date, time, available memory, things like that. So some systems also support registry, which is used to store and retrieve configuration information. So then we also want a category for file modification, programming language support, so compilers, assemblers, debuggers, interpreters, for anything we might want, C, C++, Java, Perl. Actually, I use half those languages. I use C and C++. We also want, some stuff for program loading and execution. We see some reoccurring things here: communication, background services. So what do I mean by background services? Constantly running system program processes known as service subsystems, or daemons. One example is the network daemon that we talked about, or we will talk about in 2.4.5. In that example, a system needed a service to listen to a network connection in order to connect. Okay, so we have some things that run in the background. So along with all these system programs that we kind of categorize, that they almost look like the classes of system calls we have. So along with these system programs, most OSs are supplied with programs that are useful for solving common problems or performing common operations. So some application programs. So not only do we have system programs to handle some of these more low-level things, we've got some higher-level apps that, for more typical things. So things like web browsers. Ubuntu comes with Firefox. Windows, like it or hate it, comes with Edge. I've never used Edge, actually. I had to use Internet Explorer when I worked at Dell, because that's what they had to use for some reason. Their internal site only worked on Internet Explorer, or it was only really compatible with Internet Explorer. Sounds like a nightmare, doesn't it? Things like word processors, text formatters, things like, is it gedit or gedit? I call it gedit. Spreadsheets, database systems, compilers like GCC, plotting, maybe some statistics stuff, and maybe solitaire, so some games. All right. Okay, and then it just talks a little bit about the differences, so between like Mac and Windows, and differences in user interfaces, and what kind of applications they come with. Nothing too interesting there. All right, so we've talked about some interesting things so far. So we've talked about system software most recently. We talked about, what makes up system software? How do we get software that does all these cool things, or all these necessary things? And we do that through system calls. And so previously we defined why do we want system calls and what do system calls do. So now let's actually look at, as I think we're getting closer to the tail end of the chapter, a little bit on operating system design and implementation. So what are our design goals? So the first problem in designing a system is to define the goals. We want to set some markers that we want to hit. At the highest level, the design of a system will be affected by the choice of hardware. So of course, if we're designing an operating system, we should be conscious of what it's going to be running on. If we're going to be running on a Raspberry Pi, well, an operating system like Windows doesn't make much sense because it's not going to fit on a Raspberry Pi. You might need a mighty big memory card or an SD card. Yeah, and then what type of work it's for. I mean, if you're doing some embedded system, you don't need a full-fledged OS, right? You need some real-time OS, some very lightweight thing. So beyond this highest design level, the requirements may be much harder to specify. The requirements can, however, be divided into two basic groups, so user goals and system goals. So users are going to want certain things in a system. The system should be convenient to use, easy to learn, reliable, safe, and fast. So anything that someone buying a computer would think of, they want these things. But, when we're talking about system design, someone says, oh, I want something that's fast and reliable and safe. Well, then the guy that's writing the system software has to go, what does safe mean? What granularity is? Do you want it to be provably safe? Do you want it to be pretty safe? There's a trade-off between safety and performance. So, of course, these specifications are not particularly useful in system design. Okay, we talked about that. So a similar set of requirements can be defined by those people who must design, create, maintain, and operate the system. So ideally, or similarly, it should be easy to design, implement, and maintain. So it's important. The maintenance is a big thing, because if there's a problem, if there's some, Windows releases patches, Linux distributions release patches, it's important that the people that are in charge of the OS can afford to spend the time to make patches. They should be able to go back to the code and be able to understand it. So, but these are also vague and can be interpreted a lot of ways. So we didn't get much better there, but we're not going to. So there is no unique solution to the problem of defining the requirements of an operating system, just like anything else. If you say build a table, there is no correct answer to building a table. There's some obviously wrong ways to build a table. There's some obviously basic parameters to building a table, but for the most part, it's pretty flexible. So for example, the requirements of VxWorks, a real-time OS, or RTOS, as it's often called, for embedded systems, is substantially different than those for MVS, or a large multi-user, multi-access operating system for IBM mainframes. So we have some tiny little board, some Raspberry Pi or something. Probably want a different operating system than an IBM mainframe. I think most people can rationalize that. So specifying and designing an operating system is a highly creative task, and then no textbook's going to tell you how to do it. But that's what software engineering is for. So if you're a software engineer here, hey, welcome. This is for you. So what do we want to design? So we want to talk about mechanisms and policies. We want to separate them. One important principle is the separation of policy from mechanism. A mechanism is how to do something, and a policy is what to do. For example, the timer construct that we saw previously last week is a mechanism for ensuring CPU protection by deciding how long the timer is set for a particular user is a policy decision. So, for some situations, we may want to, keep the user on a short leash, so they can't just hog everything. So they have a very small window. But, in other systems, we may go, well, give them some leeway. It's not that big of a deal. So that's how what we're doing is we're still implementing a timer, but the granularity of that timer is kind of changing, or how long we're waiting on that timer is changing, which is important for flexibility. We want to be able to change things, of course. So policies are likely to change across places over time. Remember, policy is the how, or no, mechanism is the how, policy is the what. In the worst case, each change in policy would require a change in the underlying mechanism. So the mechanism would be the timer, and the policy is, say, 5 seconds, or 5 milliseconds, or 0.5 milliseconds, or 5 microseconds. A general mechanism, insensitive to change in policy, would be more desirable. So we want to be able to change the policy without it affecting the mechanism. Okay. So if the mechanism is properly separated, it can be used either to support a policy decision that is for I/O intensive things, should have priority over CPU intensive ones, or to support the opposite policy. So ideally, we have something very general. So if we talk about microkernel-based operating systems, like, is it the cell 4 microkernel? So I think it's like cell 4, or maybe it's no, maybe it's something like SE. Maybe it's this cell 4 microkernel. That's like a secure microkernel. I always wanted to learn more about it, but I haven't had the time. So microkernel-based operating systems. So in 2.7, so we're not there yet. So we'll talk about it a little bit. Take the separation of mechanisms and policy to one extreme by implementing a basic set of primitive building blocks. So these blocks are almost policy-free, allowing more advanced mechanisms and policies to be added via user-created modules or user programs themselves. As an example, consider the history of Unix. First, it had a time-sharing scheduler. In the latest version of Solaris, scheduling is controlled by loadable tables. Depending on the table currently loaded, the system can be time-sharing, batch processing, real-time, fair sharing, or any combination. So if we want to actually take a look at this real quick, we can at least pull up the code. So if we go to this great site, let's see if I still remember where it is. So I want to go to kernel, I want to go to schedule, and then I want, so here's all the different schedulers that we have. So we have the fair scheduler, often called CFS or completely fair scheduler. But we also have a real-time scheduler in here, defined under rt.c. So it's a real-time scheduling class. So this is what we're talking about. We have, and we can define our own scheduler in here. I forgot, there's a file in here that we have to change that actually sets the priority of these schedulers, but I won't waste time trying to find it now. But basically the idea is simple. We can just write a C program for a scheduler, implement it, recompile the kernel, and hey, we have our own scheduler now. Isn't that cool? So we just really want to, stress this split of how versus what. And so if you remember, how is the mechanism, that's what is being done. Or sorry, how is the mechanism, so it's, the underlying way that something's being executed. But then what we're doing with this mechanism is the policy. Okay. So now that we talked about, what did we just talk about? What was this? Mechanisms and policies. Okay. So now let's talk about implementation. So once an OS is designed, it must be implemented. So just having this, kind of sketch of an OS is fine, but we can't run a sketch. So because operating systems are collections of programs written by many people over a long period of time, it's difficult to make general statements about how they're implemented. So early OSs were written in assembly language. That sounds awful. Now, although operating systems are still written in assembly language, most are written in high-level languages like C or C++. So if we went back and we looked at that site again, and I think we showed it earlier, there's some ARM assembly in there. So we have to have assembly at some level because we have to do some stuff with the hardware. So, it's not all C and C++ still. There is still a market for people that know, assembly language. So actually an OS can be written in more than one language. The lowest levels of the kernel might be in assembly, which is the case for something like Linux. And I think probably even Windows. I think Windows probably is even, or it has to be, x86. High-level routines might be in C, and system programs might be in C or C++. And interpreted scripting languages like Perl or Python, or in shell scripts. In fact, Linux distro probably includes programs written in all of these languages. So I know for sure assembly C and C++. I don't actually know about Perl or Python, but I've never actually looked at that section of Linux. Okay. So the first system, if it's not written in assembly language, was probably MCP, or Master Control Program, from Burroughs Computers. So it was written in Algol and Multics. I've never heard of these. Oh, it's MIT stuff. Okay. So Linux and Windows are written mainly in C. And there's some small sections of assembly code for device drivers and for saving and restoring the state of registers. and for things like page faulting. So the advantage of using high-level language is that it's easier, of course, or at least a systems implementation language, is that it's at the same granularity of the language used for application programs. So it can be written faster and is more compact. Also, it's much easier to port or to move to other hardware if it's written in another high-level language. So if we take the original, MS-DOS for an example, which is written in Intel 8088 assembly language for the 8088 processor. So, it runs on Intel x86 family CPUs, but yeah, that's about it. Maybe on an emulator that emulates x86 instructions to run on other CPUs, but not natively, and it's going to be a heck of a lot slower because we're emulating them. So as we mentioned, emulators are programs that duplicate the functionality of one system on another system. But, Linux, on the other hand, is written mostly in C and is available natively on a number of different CPUs. So on x86, on SPARC, and even on PowerPC. I would love to use something that's PowerPC or SPARC. I've only ever used x86 things. So the only possible disadvantage of implementing an operating system in a high-level language is reduced speed and increased storage requirements. But, hey, we've got some pretty dense memory nowadays, so we're not doing too bad. And we can optimize things pretty well now. And compilers are pretty good, so reduced speed isn't even that much of an issue. So although an expert assembly language programmer can produce efficient small routines for large programs, a modern compiler can perform complex analysis and apply sophisticated optimizations to produce excellent code. So one of the interesting things, if we talk about, cuBLAS and cuDNN, these libraries from NVIDIA, these are actually written in NVIDIA assembly called SAS. So NVIDIA still writes things natively in SAS. Isn't that amazing? They write assembly for entire libraries. Their machine learning libraries are written entirely in assembly. That's incredible to me. But that's why they own the market. So as is true in other systems, major performance improvements in operating systems is likely to be the result of better data structures and algorithms than excellent assembly language code. People can't just churn out assembly language code for an entire operating system. We've got to find other ways. Okay. So let's get to 2.7. So we talked about operating system design. Now let's talk a little bit about operating system structure. So a system as large and complex as a modern OS must be engineered carefully if it's to function properly. So we got a lot of moving parts. A common approach is to partition the task into small components or modules rather than have one monolithic system. If you're working with like a simulator or something, generally the entire simulator is one giant C file or C++ file. You want to break things up. You want to use some abstraction here. Abstraction's a common thing in every part of engineering. How many ye's did I miss? A lot of them. But guess what? You're here now. The VOD will always be available. And guess what? We're still going. We're talking about operating system structure. Okay. All right. So we talked in chapter 1 a little bit about the components of our operating system, but we should probably talk about it a little bit more, don't you think? So if we look at something like the MS-DOS layer structure, at the very top, of course, we have apps. We have application programs that talk to some resident system program that talk to MS-DOS drivers that talk directly to, some ROM, BIOS, device drivers. But we also see that each of these layers has connections to these device drivers as well. So many operating systems do not have well-defined structures. Frequently, such systems started as a small, simple, and limited system, and then grew beyond their original scope. So MS-DOS is such a system. It was designed and implemented by a few people who had no idea it would become popular. And here's a funny thing. This is actually a problem that Linux is facing right now. Because Linux was designed not for, a data center. It was designed for personal computing. So there was even a paper recently that said something about, I think the title of the paper was Linux Scheduling, a Decade of Wasted Cores. It wasn't designed for data center use. It was designed for consumer level computing. So DOS was written to provide most functionality in the least space. So it was not carefully divided into modules. So that was that structure we looked at. So the interfaces and levels of functionality are not well specified or separated. For instance, application programs were able to access the basic I/O routines to write directly to the display and disk drives. So such freedom leaves MS-DOS vulnerable to malicious programs, causing entire system crashes because, hey, some regular app can just talk to these device drivers. Doesn't seem great. Why is it so popular in data center usage? I mean, it's gotten better, but it's a real big problem that Linux has, though, is because if it wants to be, it could be way better for data centers. The problem is, right now, in order for it to be good in data centers, it's basically patch on top of, patch on top of, patch on top of, to add things that make it good for data centers. But that's not the original design. So, yeah, it's not the original design. So, hey, it could, if you, you could make the argument for everything. If you designed GPUs from the ground up to be secure platforms, then security wouldn't be an issue on GPUs. But I can't really answer why it's so popular in data center usage. Maybe it's cheaper than Windows. Maybe it's cheaper than Windows. Maybe people don't like having to use PowerShell. Idra, do you like using PowerShell? Have you ever used PowerShell? I worked on Windows servers when I was at Dell. Well, I worked on all types of servers. I was doing server storage. But I worked a lot on like Windows Server Core. You don't want to work on Windows Server Core. It's awful. Nothing works. Or nothing works how you want it to. Yes, I did actually a few times, but I'm probably better with Bash. Everyone's better with Bash because Bash is intuitive and it's supported. So another example of a limited structuring is the original Unix operating system. So like DOS, Unix was initially was limited by hardware functionality. It consists of two separable parts, the kernel and system programs, so kernel space and user space. The kernel is further separated into a series of interfaces and device drivers, which have been added and expanded over the years as Unix has evolved. We can view the traditional Unix OS as being layered to some extent, as shown in this figure right here. So we have shell, commands, compilers, interpreters, and libraries, some syscall interface, where we signal terminal handling, character I/O, system, terminal drivers, file system, swapping block I/O, system, disk, and tape drivers, scheduling policies are all in the kernel. And then it has an interface to the hardware. So everything below the syscall interface and above the physical hardware is the kernel. So this typical Linux kernel resides in this space. The kernel provides the file system, CPU scheduling and memory management, and other OS functions through the system calls. Taken in sum, this is an enormous amount of functionality to be combined into that one level. So yeah, Idra, this is kind of the main thing, is that really no operating system is designed well for data center stuff because I shouldn't say no operating system. There's probably some unique operating system or some academic one that is. But it's this idea of having the kernel just take care of all of these things, and you don't have this. Is this a textbook? Yeah, this is operating system concepts. It's the dinosaur book of operating systems. So let's talk about instead a layered approach. So with proper hardware support, operating systems can be broken into pieces that are smaller and more appropriate to those allowed in the original DOS and Unix systems. The operating system can then retain a much greater control over the computer and over the applications that make use of that computer. So implementers have more freedom in changing the inner workings of the system and creating modular operating systems. So if we create a more layered approach, this just builds on that idea of abstraction. So if everything kind of isn't intertwined in one giant mess in something called the kernel, well, it's easier to plug and play things. So a system can be made modular in many ways. So a layered approach is one way, in which the OS is broken into a number of layers or levels. So the bottom layer is the hardware, and then the highest layer is, of course, the user interface. And so here we have some basic description. This bullseye is something that's common to many different areas if we're talking about layers of abstraction. I was actually confused when I first looked at this book because I have a digital design book with Verilog that in the first chapter it uses a figure exactly like this to talk about the different layers of abstraction writing hardware description language code. So an operating system layer is an implementation of an abstract object made up of data and the operations it can use to manipulate those data. Not a very clear thing there, so let's try to deconstruct it. So we have data, and then we have operations to manipulate that data, and we'll just consider that a layer. So we'll just section off some of the data and some of the operations per each layer. A typical operating system layer, say M, consists of data structures and a set of routines that can be invoked by higher level layers. And then layer M, in turn, can invoke operations on lower level layers. So the main advantage to a layered approach is, of course, simplicity of construction and debugging. So if we isolate these layers and the functions to these layers, then we don't have to worry about debugging the entire thing. We can debug a layer, or we can debug the hooks that we use to interface between layers. So the first layer can be debugged without any concern for the rest of the system, because by definition, it uses only the basic hardware, which is assumed correct. This is an assumption that we make a lot in software. We make the assumption that, or all the time, because it's relatively true and common, that there's probably not something wrong with the hardware. When I was doing embedded systems work, it was one of the things when I wasn't a TA, but I helped a lot in that class. And what I would always have to do is, people would come up to me and say, oh, I think something's wrong with the chip I have. I think something's wrong with the board. And most of the time I would just say, no, probably just the code. Probably isn't a hardware problem. Okay. And then the second layer is debugged and so on. So we debug layer by layer, which is the idea we're trying to get across. So each layer is implemented with only the operations provided by lower level layers. A layer does not need to know how these operations are implemented. It only needs to know what these operations do. So this is, like an API, like we were talking about earlier. We don't care about how, when we make an API call, we don't care about what it's doing. When I say do CUDA malloc, I don't care what's happening on the GPU. I just care that I've allocated memory in the GPU. And I just care that I get some response back saying, hey, it passed. You allocated this size of memory. So the major difficulty with the layered approach involves appropriately defining the various layers. So, we don't get so lucky where we can just say, hey, I'm going to use a 10-layer model, and then all the layers are going to be used. And this is exactly the case with something like in networking. So like the OSI 7-layer model. People are haughtily debate the OSI model and why it's called this, because not all of the 7 layers are required. You can bypass some of the layers. They're not necessary. So, we run into this problem a lot. So let's see. So because a layer can only use the lower level layers, careful planning is necessary. For example, a device driver for the backing store, so disk space used by virtual memory algorithms, must be at a lower level than the memory management routines, because memory management requires the ability to use the backing store. So, we find ourselves in this situation where we have like a tangled web, and we have to untangle it and figure out where all the dependencies are. And once we get to a really large operating system that has a lot of moving parts, untangling that web can be pretty difficult. But then we have other things that are but we have things other than memory management, like we're talking about, that aren't so obvious. So the backing store driver would normally be above the CPU scheduler, because the driver may need to wait for I/O, and the CPU can be rescheduled during this time. But on a large system, the CPU schedule may have more information about all the active processes that can fit in memory. So this information may need to be swapped in and out of memory, requiring the backing store to deliver information to the scheduler. So we see that we have some nasty interconnection things that make this layering difficult. And what's a final problem with layered implementations is that they tend to be less efficient than other types. For instance, when a user program executes an I/O operation, it executes a system call that is trapped by the I/O layer, which calls a memory management layer, which calls the scheduling layer, which is passed to the hardware. So, if we just had a more direct connection, we don't have to go through, 3-4 layers. So, there's some minuses as well. So, they've caused a small backlash against layering in recent years, apparently. But fewer layers with more functionality are being designed, providing most of the advantages of modularized code while avoiding the problems of layer definition interaction. So, if instead of using 10 layers or something crazy, if we decided to use maybe 2 layers, 3 layers, that might be good enough. We might be able to get enough separation, and we don't need to worry as much about, this fine-grained untangling of dependencies. Now we're finally getting into microkernels. So something different. So we've already seen kernels can become large and difficult to manage. So in the 1980s at CMU, Carnegie Mellon University, developed an operating system called Mach that modularized the kernel using the microkernel approach. This method structures the OS by removing all non-essential components from the kernel and implementing them as system and user level programs. So the result is a small kernel that we can plug and play things if they're needed. So there's little consensus regarding which services should remain in the kernel and which should be implemented in the user space. So this is always an argument of what people find necessary. What's necessary for one person isn't necessary for everyone. So they typically provide minimal process and memory management in addition to communication facility. So here we have a typical microkernel. So in the microkernel, we'll have scheduling, we'll have memory management, and we'll have some stuff for inter-process communication, so shared memory or message passing. But, device drivers will be in the user space, file system will be in the user space, and the application programs will all be in the user space, while the kernel mode is, very small and isolated. So the main function of the microkernel is to provide communication between client program and various services. Okay, so it doesn't use shared memory, it uses message passing. We already talked about message passing earlier. It's the idea of having some shared mailbox where 2 processes can leave structured messages and then they check the mailbox. Okay. So what's the benefit of using a microkernel? It seems like we're stripping out all the functionality, Why would we do this? So it makes extending the operating system easier. If everything's a user space program, well, hey, it's easy. They're just added as a user space program, and they don't require modification of the kernel because the kernel's tiny. When the kernel does have to be modified, the changes tend to be fewer. Because we have a tiny kernel, probably won't take that long to modify it. So the OS is easier to port because it's small, and also provides more security and reliability since most services are running as user rather than kernel processes. So it's in the user space, not in the kernel space. If a service fails, the rest of the operating system remains untouched. So yeah, this is a problem with Spectre and Meltdown have this problem. So when it's, like I said in probably a previous stream, Spectre and Meltdown rely on exploiting speculative execution and out-of-order execution. So what basically happens is that in kernel space, during this speculative execution, they intentionally trigger an exception, and this changes some kernel space state. How many chapters? What do you mean? How many chapters have I gone through? How many chapters are there in this book? How many chapters are in another book? Are here in this book? That's a good question. I think it's like 15 or 16. There's quite a few. I know they mentioned like chapters like 14 or 15 earlier in this chapter, but I don't exactly know the higher number. I think it's like 16 or 17 though. But quite a few. It's a big book. It's the book for operating systems, so it's got to be big. Okay. So what's some contemporary operating systems that have used the microkernel approach? So True64, formerly Digital Unix, provides a Unix interface to the user, but is implemented with the mock kernel. So the mock kernel maps Unix system calls into messages to the appropriate user level services. And then the Mac OS X kernel, formerly known or also known as Darwin, is also partly based on the mock microkernel. Interesting, I didn't know that. Another example is QNX. QNX Neutrino microkernel provides services for message passing and process scheduling, and handles some low-level network communication and hardware interrupts. And then everything else is outside the kernel. Okay. So unfortunately, the performance of microkernels can suffer due to increased system function overhead. Sure, makes sense. Consider the history of Windows NT. The first release had a layered microkernel organization. The version's performance was low compared to even that of Windows 95. Windows NT 4.0 partially corrected the performance by moving layers from the user space to the kernel space and integrating more closely. By the time XP was designed, architecture had become more monolithic than microkernel. So that's interesting. We saw that Windows even at a point adopted a microkernel type design, but has since moved to something more monolithic. Now Windows is just a mess, a monolithic mess. Well, that'll be the catchphrase of the channel when we talk about Windows. It'll be that this is Windows. It's a monolithic mess. Okay. At least the registry is. The Windows registry. Okay, so let's talk about modules now. So what did we talk about here? We talked about microkernel, so let's talk about modules now. So the best methodology, or perhaps, it's always arguable, for operating system design involves loadable kernel modules. So here the kernel has a set of core components and links in additional services via modules at boot time or maybe at run time. And this design is common in things like Solaris, Linux, Mac, OS X, and even Windows. So the idea behind the design is for the kernel to provide core services, but the other services are done dynamically. So if we need a service, we load it in. For example, we might build a CPU scheduling and memory management algorithm directly into the kernel and add support for different file systems by way of loadable modules. Is an equivalent Linux to the Windows registry? Is it just like the parameters I can set set in the console? What do you mean by parameters? You mean like environment variables? I mean, it fundamentally is just a bunch of settings, right? Um, but the thing is, it has all settings, right? It has settings for like every previous version of Windows. Yeah, I don't. Linux doesn't implement something like that. No. Yeah, it definitely doesn't implement something like that. Yeah, it's just like settings. It's just like low level setting information. But the thing is, it's low level setting information for everything and for like every. I never really got why it's such a huge structure of stuff because it has information about everything. So, for every version of Windows. So Windows 10 has Windows 8 stuff and Windows 7 stuff and Windows XP stuff and probably Windows Vista stuff and probably some Windows ME stuff and Windows 95 stuff maybe. It has a lot of stuff in it. That's why you can run things in compatibility mode. At least that's how I understand it. But I'm not a master of the Windows registry. But it'd be an interesting thing to look up. But no, Linux definitely doesn't have something like the Windows registry or like like the Windows registry. No. Okay. So with these loadable modules, it looks like a layered system in that each kernel section has defined protected interfaces. But it's more flexible than a layered system because a module can call any other module. So there's not this strict isolation between modules now and these set layers. Now we just have these kind of things that we can load in and out, but they can talk to each other now. Okay, so similar to a microkernel. So here we have an example with Solaris. So we have the core Solaris kernel, but then we have loadable modules for file systems. So if you want a new file system, you just load it in. Loadable syscalls, executable formats, stream modules, miscellaneous things, device and bus drivers, and scheduling classes. Neat. So Linux also uses loadable kernel modules primarily for supporting device drivers and file systems. And then that gets covered at the end of this chapter. Well, isn't that nice? We might not go over that though, since that would probably just that'll be operating system specific, like Linux specific, which that's never that interesting. I mean, that's like reading a manual. So let's talk about hybrid systems. Neat. So systems that, combination of these core ideas that we've been talking about. So in practice, a few operating systems adopt a single, strictly defined structure. Instead, they combine different structures. So, we pick and choose as we please, resulting in hybrid systems. So Linux and Solaris are both monolithic because having the operating system in a single address space provides very efficient performance. However, they're also modular because you can dynamically add things to the kernel. And then Windows as well is largely monolithic for performance, but it retains some behavior typical of microkernel systems. So support for separate subsystems known as operating system personalities. That's neat. I've never heard of that before. That run in user mode. Windows system also provides support for dynamically loaded kernel modules. We provide case studies for Linux and Windows 7 in chapters 18 and 19, respectively. So Codeman TV, if you're still here, apparently there's at least 19 chapters in the book. Okay, so more hybrid systems. So they've got a brief note on OS X and iOS, but there's not much point talking about specifics. So here's at least the Mac OS X structure. So we have some GUI interface called Aqua, and then we have some application environment services. So this is like user space, or is analogous to user space. So with things like QuickTime and Java. But then we actually have like the mock kernel environment, And then below that is the IOKit and kernel extensions. Okay. Yeah. And then iOS is, pretty structured. You've got some touch, media services, core service, and core OS. Well, that's pretty layered to me. Android. Android OS designed by, well, you can basically say Google made Android. Where iOS is designed to run on Apple mobile devices, and it's closed sourced. Android runs on, it's open source, okay. Android is similar to iOS in that it's a layered stack of software with a rich set of frameworks for developing mobile applications. So at the bottom, you of course have the Linux kernel. It is a Linux-based operating system, but it's been modified, of course. I mean, core is Linux, but modifications are always necessary. So it's used mainly for processing memory and device driver support. So the Android runtime environment includes a core set of libraries, as well as a Dalvik virtual machine, software designs for Android, device develops applications in the Java language. Okay, it's not that interesting. So let's just look at the structure for a little bit. So you have applications, and then below that you have, of course, the application framework. Then you have these core libraries for the Android runtime and this Dalvik virtual machine. But then you also have these other libraries, so common things like libc that you need, but also things like OpenGL, right? OpenGL is actually something that I found to be extremely dangerous. If you look up the exploits that you can find with OpenGL, it's ridiculous, just arbitrary code execution. And mobile devices are a very interesting area for security with me, just because of how buggy these device drivers are. It's actually incredible. Maybe we'll go over a paper that details that. I've already gone over one, I know, but maybe we'll go over another sometime. Okay. So now let's talk about the worst thing in the world, is how do we debug an operating system, right? So I'll let you in on a secret. If you're debugging an operating system on hardware, you're going to have a bad time. And this is because what happens if you're making a modification to an operating system, and you're making a modification to an operating system, and you boot it, and you say, I want to use GDB to debug this. You try to boot it, and it doesn't boot because you messed up the operating system, so it doesn't boot. Well, you can't use GDB if it doesn't boot. So you can't use GDB, can't use printk. You're in some trouble there. There's some very clever ways to do debugging, but I'm certainly not clever enough to do them, or at least I'm not an operating systems researcher, so I don't have to do them. I let the operating systems people take care of that. So we already talked about debugging in terms of fixing errors in a subsystem, and then also doing things like performance tuning, and also analyzing bottlenecks. So where are we actually getting stuck here? Are we stuck at, we're running out of compute? Are we stuck at too much traffic at the memory system? Where are we stuck at? Maybe our scheduling is bad. I mean, there's a paper that seems to think so. It says a decade of wasted cores. So let's look at failure analysis. So if a process fails, most operating systems write an error information in a log file to alert the system operators. The operating system can also take a core dump, which basically captures the memory of the process and stores it for later analysis. So it's fine if the operating system crashes before it's, or after it's booted. So memory was referred to as a core in the early days, so that's why we call it a core dump. Okay. So debugging user-level process code is a challenge. So the OS kernel debugging is even more complex. So if you thought, debugging your C code was bad, let's talk about debugging an operating system. So the first thing you have to be concerned with is the size and complexity of the kernel and its control of the hardware. So we're not just talking about debugging some software that gets compiled, right? We're also talking about debugging maybe assembly that we've changed. So actually talking with the actually talking with the, what's it called? What am I trying to say? Actually talking with the hardware itself, the actual instruction set. C++ compiling errors feels good, man. Listen, nothing makes me happier than debugging a seg fault now after having to debug in my kernel schedule or my process scheduler that I made, causing the OS to not boot. It's a little. I feel I'm grateful every single day. So, a failure in the kernel is called a crash, and when a crash occurs, information is saved to a log file. So crash dump. Okay. So OS debugging and process debugging frequently use different tools and techniques due to the very different nature of the task. So kernel failure in the file system code would make it risky for the kernel to try to save its state to a file before rebooting. So a common technique is to save the kernel memory state to a section of disk set aside for this purpose that contains no file system. If the kernel detects an unrecoverable error, it writes the entire contents of memory, or at least the kernel in parts, to system memory to the disk area. When the system reboots, the process runs to gather the data from the area and write it to a crash dump file. So what's Kernighan's law? So Kernighan's law, let's see if we get some key insights into debugging. So debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. I love this law. This is my new fit. This is the new stream model. If you write clever code, or you write code as cleverly as possible, you are by definition not smart enough to debug it. I love it. That's great. Okay, let's talk about performance tuning now. So we talked about debugging a little bit. It didn't get into any of the interesting parts of debugging. Let's talk about performance tuning though. So we mentioned earlier that performance tuning seeks to improve performance by removing processing bottlenecks. To identify bottlenecks, we must be able to monitor system performance. Okay, so let's see. So this is, tracing is oftentimes what, finding performance bottlenecks means. We trace an application. In a number of, or profile an application. In a number of systems, the operating system does this by producing trace listings of system behavior. All interesting events are logged, and their time and important parameters are written to a file. Okay. So another approach of performance tuning uses single-purpose interactive tools that allow users and administrators to question the state of various system components to look for bottlenecks. So things like the top command in Linux. So if you do top, you get a list of the currently running processes, and you can see exactly what resources they're using. I made some ridiculously big, like 2.5 gig log file, and I tried to open it with Vim, and well, it took forever, and so I ended up just having to kill it. But you have to, when you do like kill-9, you have to use top to figure out what the process ID is. So hey, there's a real-world use of top. So other tools display the state of disk I/O memory allocation and network traffic. So the task manager is a similar tool in Windows to top. I prefer top because, well, I use a command line and it's easy. So making operating systems easier to understand, debug, and tune as they run is an active area of research and implementation. So one thing you'll find is that there are no good debugging tools. They don't exist, really. GDB is pretty good, but for a lot of areas like debugging a CUDA application that runs on a GPU, no, there's no good debugging for that. So let's talk about dtrace now. So dtrace dynamically adds probes to a running system, both in user process and in kernel. And these probes can be queried via the deprogramming language to determine an astonishing amount about the kernel and system state. So for example, 220 follows an application. So let's just look at 220. So where's 220? Okay. So it follows all the system calls. Okay. So events queued, IO control, getF, set active file descriptor, release F, CPU broadcast, IO control. Yeah. So it gives a little arrow like to and from, and then it also says whether it's user space or whether it's kernel space. Okay. So debugging the interactions between user level and kernel level code is nearly impossible without a toolset that understands both sets of code. Until the dchase framework and tools became available with Solaris 10, kernel debugging was usually shrouded in mystery and accomplished via happenstance and archaic code and tools. So basically magic. So for example, CPUs have a breakpoint feature that will halt execution and allow a debugger to examine the state of the system. Then execution can continue. Talk about profiling, which periodically samples the instruction pointer to determine which code is being executed and shows statistical trends, but not individual activities. So good for some things, bad for others. Isn't that life? So in contrast, dtrace runs in production systems. So systems running important or critical applications and causes no harm to the system. It slows activities while enabled, but after execution, it resets the system to its pre-debugging state, and well, it just goes ahead. Works just fine. It can also delve deep into code showing individual CPU instructions or kernel subroutine activities. So dtrace is composed of a compiler, a framework, providers of probes written within that framework, and consumers of those probes. Is dtrace similar to kprobes? I think it probably is. Kprobes is another interface that I don't think they talk about in here. But it's a way of probing kernel things, and so you can instrument routines yourself. Actually, you can catch things, and you can instrument these kernel probes, and then you instrument code at certain breakpoints in the program and and execute arbitrary code. Okay, so let's see. Anything else interesting? So dtrace features a compiler that generates a bytecode that is run in the kernel, and then it's assured to be safe by the compiler. So we get some safety guarantees by a compiler. That's always nice. For example, no loops are allowed, so we're not going to get any infinite loops. And only specific kernel state modifications are allowed when specifically requested. Only users with dtrace privileges, so that's not really that safe of a thing. That basically just says that you have to be root in order to use it. So, well, if someone already has root and they're going to do malicious damage, well, they probably could. So a dtrace consumer is code that is interested in a probe and its results. A consumer requests that a provider create one or more probes. When a probe fires, it emits data that are managed by the kernel. And then within the kernel, actions called enabling control blocks, or ECBs, are performed when probes fire. One probe can cause multiple ECBs to execute if more than one consumer is interested in that probe. Okay, so a pretty simple concept here. Basically, we put probes throughout some program that we're profiling, and then when we hit those probes, it fires off and it does something. It does something that we specify, maybe. Because it's written in D language, so we write the code. Okay. So once the probe consumer terminates, we get rid of it, remove the ECBs, and if there are no ECBs consuming a probe, the probe is removed. That involves rewriting the code to remove the dtrace probe. So we got some self-modification of code here. That's pretty interesting. Dtrace takes care to ensure that probes do not use too much memory or CPU capacity, which could harm a running system. So if we're doing something like profiling or debugging, we want to make sure that we're not killing system performance, as a result. Okay. I think this is just an example. So now let's talk about something a little more interesting than talking about this dprobe thing. Let's talk about operating system generation. So it's possible to design code and implement an OS specifically for one machine at one site. More commonly, however, OSs, they're generally designed to run on any class of machine at a variety of sites and a variety of peripheral configurations. So if somebody wants, a mouse, a keyboard, and a drawing tablet like me, well, hey, you can have it. The system must then be configured or generated for each specific computer site, so often known as system generation, sysgen. So the operating system is normally distributed on disk, on CD-ROM or DVD-ROM, or as an ISO image. So this is, of course, an ISO. To generate the system, we use a special program. So this sysgen program reads from a given file or asks the operator for a system for information concerning the specific configuration of the hardware system, or probes the hardware directly to determine what components there are. Usually it does this automatically. So the following kinds of information must be determined. So we of course need what CPU is being used. We also need what options are installed. So extended instruction sets. So something like Intel processors have the instruction sets are extended for what are they called? AES instructions. So encryption instructions. For most CPU system, each CPU for multiple CPU systems, each CPU may be described. But then we also need to know some more, simple things. So how will the boot disk be formatted? How many sections or partitions will it be separated into? And what will go to every partition? We need to know things about how this is being stored. So how much memory is available? Another key thing, if we're going to be playing around with memory, loading things into memory, executing things from memory, we need to know how much is available. How much can I, soak up? Some systems will determine this value themselves by referencing memory location after memory location until it gets in a legal address. So I think this is usually called pointer chasing. This procedure defines the final legal address and hence the amount of available memory. We also need to know what devices are available. So we need to know, what type of I/O there is. And then we need to assign things like device numbers and interrupt numbers, the device type and model, and any special characteristics. So if we plug in the keyboard, we want to know, we hope that it knows what keys are on the keyboard, right? We don't want it to forget that, hey, there's no space on the keyboard. So what operating system options are desired? So these are more customized. So what do we want with our operating system? Or parameter values are used. Something that most general users don't really care about, but if you're doing something more specific, generally you're changing some OS parameters. So these options might include how many buffers, which size, what type of CPU scheduling algorithm is desired. So in Linux, it's by default the completely fair scheduler. What is the maximum number of processes to be supported, and so on. Okay. So after we have all this information, it can be used in several ways. A sysadmin can use it to modify or a copy of the source code of the operating system. The operating system then is completely compiled, data declarations, initializations, constants, etc., etc. At a slightly less tailored level, the system description can lead to the creation of tables and selection of modules from a precompiled library. So we can make it a little more portable by saying, here's a selection of things, instead of having something that's set. And then at the other extreme, we can construct a system that's completely table-driven. So all the code is always part of the system, and selection occurs at execution time rather than compile or link time. So system generation involves simply creating the appropriate tables to the described system. So the far extreme from a completely customized set system. Okay. Not much else interesting here. So let's go ahead and start at something far more interesting, which is system boot. Now, if you ever want to get a job, something computer engineering related, they're probably going to ask you about how does the system boot? It's a pretty typical question in a lot of areas. So after an operating system is generated, it must be made available for use by the hardware. But the hardware has to know where the kernel is, though, or how to load the kernel. In a process called booting the system. So on most computer systems, there's a small piece of code called the bootstrap program or bootstrap loader. It does exactly what you think of it does. It pulls everything up just like bootstraps. So it locates the kernel, loads it into memory, and starts execution. Some computer systems, such as PCs, use a two-step process in which a simple bootstrap loader fetches more complex boot program from disk, which in turn loads the kernel. So basically what happens is, on one extreme, you have the bootstrap that just pulls in the entire kernel at boot time. The second thing is you have some tiny code that's in the two-step process. You have a simple bootstrap that pulls in the real, bootstrap loader that then loads in the kernel. So when a CPU receives a reset event when powered up or rebooted, the instruction register is loaded with a predefined memory location and starts execution there. So that memory location is going to be where this bootstrap program is. So something like a ROM or an EEPROM or something. Of course not RAM, because RAM's volatile, so at boot time you have no idea what's in there. ROM is convenient because it needs no initialization and cannot easily be infected by a computer virus. But I think people have done that though. But generally that's a little harder to do. So some systems, like cell phones, tablets, game consoles, store the entire OS in ROM. It's suitable for small OSs, simple supporting hardware and rugged operation, but the problem with this approach is changing the bootstrap code. It requires changing the ROM hardware chips. So instead they use EEPROM, which is just erasable programmable read-only memory. EEPROM, I think, just stands for electronically erasable programmable read-only memory. So we call this ROM, or the code on this ROM, firmware, since their characteristics fall somewhere between hardware and software. So it's not quite hard, not quite soft, so we call it firm. So if you ever wondered where the term firmware comes from, well, thanks for joining the stream. There's your answer. So a problem with firmware in general is that executing code there is slower than executing it in RAM. Some systems store their operating system firmware and a copy it in RAM for fast execution. But then the final issue with firmware is it's relatively expensive, so usually only a small amount is available. Okay. So for large operating systems, so things like Windows, Mac, Unix, or the ones that change frequently, the bootstrap loader is stored in firmware and the operating system is on disk. In this case, the bootstrap runs diagnostics and has a bit of code that can read a single block at a fixed location, say block 0, from disk into memory, and execute code from the boot block. So this is that two-step process we were talking about. We load in a single block. That block contains information on, okay, what else to do? And then that kind of takes on and self-perpetuates. So more typically, it is simple code. Let's see. So the program stored in boot block may be sophisticated, but typically it's simple code and fits in a single disk block. And knows only the address on disk and the length of the remainder of the bootstrap program. So Grub is an example of an open source bootstrap program used by Linux. All of the disk-bound bootstrap and the operating system itself can be easily changed by writing a new version to disk. A disk that has a boot partition called a boot disk or a system disk. So when we talk about a boot disk or system disk, we're talking about what's being actually pointed to by some bootstrap program that has the boot block on it. So now that the full bootstrap program has been loaded, it can traverse the file system, find the OS kernel, load to memory, and eventually begin execution, start running, doing whatever it needs to do. Pretty cool. We went through the entire boot process. So now if you get that question in an interview, guess what? You've got the job now. Allow me to shake your hand and congratulate you. You'll be on your way to sitting at a desk complaining about how you hate your job in no time. Okay. So now that we've kind of finished up summarize what we've gone over. What have we talked about today? We've talked a lot about syscalls and a lot about operating systems, which is a good thing because this is an operating systems book. So let's see. So we saw that operating systems provide a number of services, from low level and even to a high level where a user can interface with it. We saw that types of requests vary according to the level that we're working on, and that system call level must be basic functions such as process control, file and device manipulation, etc. But high-level requests satisfied by the command interpreter or system programs are translated into syscalls. So we're at a high level. We don't care about what the low level's doing. We just have these nice hooks into the program. We saw that throughout the entire design cycle, we've got to carefully separate policy from implementation detail or mechanisms. So how we do something, so say if we're implementing timers, must be separated pretty cleanly from the policy. So timers for 5 seconds. So the 5-second portion should be separate from the timer for maximum flexibility if we want to change policy later. We saw that a large and complex and modern operating systems have to be engineered carefully, and that modularity is generally a good idea, but we really want to, do this mix between monolithic and modular. We saw that debugging is bad and can be accomplished through debuggers and other tools to analyze core dumps, such as dtrace. We didn't see what changing operating system code will do. We just saw what happens when the kernel crashes. So those are two very different things. We also saw that to create an operating system for a particular machine configuration, we've got to do some system generation so we know what we're targeting and certain parameters that we want to load. And we saw how the bootstrap can execute the operating system directly if the operating system is also in firmware, or we can do some sequence of loading in some boot block to find the operating system. And there we have it. We had another wonderful day talking about operating systems. I'm just so glad that I got to share it with all of you today. How is everyone feeling today? Is everyone having a wonderful day? I've got a record 9 viewers in chat right now. I saw I had like 16 earlier. We're hitting the big numbers today. Great, right? If you ever feel like donating, I ask no more per day than $3 for coffee. That's as much as I'll ever ask you for. If you want to donate more, you're more than welcome to, but I put it as a suggestion. If you want to buy me a cup of coffee at the end of a long night, I leave that to you. If you want to follow me on Twitter, follow me on Twitch, follow me on YouTube. All the links are below. I will never put any of this content behind paywalls. You never have to worry about that. There will be no Patreon exclusives. In my eyes, all of you are exclusive. Yeah. Andrew, you're a big boy now. You know all about how operating systems boot, and you know about some design principles for operating systems. Don't you feel ready to ace that interview? How does everyone feel? Is everyone ready to ace that interview? I know I'm ready to ace that interview. In fact, what I'm ready to ace is my qualifying exam. I have chosen operating systems, computer networks, computer architecture, and compilers as 4 primary areas for my qualifying exam. And then for my secondary areas, I've chosen an automatic control area and a VLSI combinational and sequential logic area. So we've got some work to do. We've got some work to do, everybody. But hey, that's why we're here. That's why we're here learning every day. Does anyone have any questions for me before we close out the stream? Don't worry, I'm not going to assign you any homework today. You guys are free from homework. Does anyone want to learn anything particularly special or new? I'm more than happy to cater my content. You just need to give me a shout. I had a fun time today. I actually enjoy operating systems. It's a little higher level than I like. I'm a computer architect, so I generally like a little more on the hardware side, but hey, we need operating systems. And in fact, the simulator I'm building, it's going to rely on a lot of infrastructure work at the operating system level. That'll be fun. The simulator, when it's done, will be fun. The work to get the simulator won't be fun. But I'm ready for it. The 20-hour days begin. Actually, they've already begun. Okay, everybody. I want to thank you all for joining me today. We've had a wonderful time. I appreciate you all being here. And guess what? I hope you all have a wonderful Thursday. It was a nice sunny day for me again. It was a little bit hotter than yesterday. We got to the 90s, but guess what? That's okay. I'm used to Texas heat, where it's hundreds, 110, so the Midwest 90-degree summer days, I'll take every single one I can get. I'm Nick from Engineering Today, and I want to thank you for joining me this evening. Have a wonderful day, everybody, and join me tomorrow. Adios.